So now we're going to switch gears and look at oxidation numbers. If you have lab, you probably looked at oxidation numbers in lab. The last class told me you didn't get any rules for the oxidation numbers. Is that correct? Oh, you have them in your lab manual. Okay. So I'm going to kind of go through the rules a little bit, and then we're just going to practice finding some oxidation numbers. Okay. So oxidation is when an atom loses some electrons. Reduction is when an atom gains electrons. Oxidation and reduction happens to individual atoms, not to the compound as a whole. So sometimes we play loosey-goosey when we're talking about it, but really we should be saying the carbon is oxidized or the chlorine is reduced, rather than talking about the whole compound. So this kind of begs the question is, how do we know how many electrons it has? So we compare the number of electrons to the number of electrons it has when it is a neutral atom, which means it's going to be a lot like charge if it is an isolated atom. And in the case of a monoatomic ion, an ion where it's just one atom with a charge on it, it's the same thing, okay? Usually we don't look at all of the electrons, we look at the valence electrons. So the valence electrons, the electrons are all in layers, kind of like an onion or an ogre. They have layers. The outside layer is called the valence layer, and we count those electrons and then compare to how many it has. That's how we determine the oxidation number. So you're not going to need to determine valence electrons right now, but just kind of briefly so you can see where we're coming from. If we look at the periodic table, we're going to see what column it's in. And so column 1 has 1 valence electron, column 2 has 2 valence electrons. Then we skip over the transition metals and go to boron. So boron is in the next kind of high column, and it's a brown one. That one is 3, and then 4, and then 5, 6, 7, 8. Okay, so we go from 1 to 8 for valence electrons. And so if the atom is assigned more electrons, then it would have a negative oxidation number. If it has less electrons, then it has more of an oxidation number, or a higher oxidation number. So in compounds, well, actually, let me first say this. Neutral elements, even polyatomic ones like oxygen is diatomic, if it is neutral and there is only one element, then it is oxidation number is 0. So if it's in a compound, or really a polyatomic ion too, any shared electrons that are between the atoms, and remember a covalent bond is 2 electrons, those get assigned to the atom that is more electronegative. So the periodic table is arranged by patterns that keep repeating. And one of the repeating patterns is that as we go across the periodic table, things become more electronegative. So that means that if I'm comparing 2 elements and I want to know which one gets those extra electrons, it's the one that is furthest to the right. Okay, so if I compare carbon and oxygen, oxygen is furthest to the right. So any shared electrons between them would be assigned to the oxygen. The oxygen gets a negative number. The carbon gets a positive number. All right, so this makes it seem like we would have to be spending a lot of time going and comparing things on the periodic table. But it turns out that there are a couple of things that are pretty consistently always true. And if we remember those things, everything else we can figure out with a little bit of math. We don't even have to know what atoms are connected together. Okay, so the first thing is, if I'm trying to figure out the oxidation numbers and I know one of the elements, I can figure out another element by knowing that they're all going to add up to whatever the overall charge is. So 0 if it's neutral, or if it's a polyatomic ion, say it's a -1 ion, they're all going to add up to -1. Okay, but I have to know something to begin with. Okay, so some elements are always going to be their common charge when they're in compounds. Now, if they're a pure element, they'll be zero. But if they're mixed with other elements, then they're always going to be that common charge. So group 1 always has what charge? That's the alkali metals, that first column, +1. So these will always be +1. Looks like an H. +1. Group 2 is going to be +2. Fluorine is going to be -1. Okay? Yes.
Does the oxidation number add up to what charge?
To whatever the charge is. So just to charge. Yeah. So like if I have nitrate, nitrate is NO3 minus. So the nitrogen and oxygens would add up to -1. Okay. All right. Most of the other rules are pretty much for your purposes still going to fit into this category, but I need to tell you the exceptions anyway. So oxygen is almost always -2. And for your purposes, you're going to assume it's -2. It is not -2 in peroxides. So a peroxide has an oxygen-oxygen single bond. And the one that you're probably familiar with is H2O2. So you use that in lab. Whenever you use peroxide, you can bet that this is going to be an oxidation reduction reaction, because the reason they're using this is so that it will either oxidize or reduce something else. Okay. So in that case, it's a -1. Okay. I won't ever give you a peroxide. So you can just kind of assume it's -2. In very, very rare circumstances, it can be a -1/2. I'm not even going to write that one down. Yeah, Isabel.
So what is are you writing O is 0 up there? What does that say? Above the minus?
This is an oxygen-oxygen single bond. That's what makes a peroxide. So oxygen doesn't normally bond to itself in compounds. If it does, and there's a single bond, it's going to be a peroxide. Okay. Hydrogen is going to be +1 with metals. For your purposes, it is always +1. I will never give it to you other than H2, where it's a pure element and it's 0. But if it is bonded to a metal, which can happen, it will be -1. All right, and then our last rule has to do with the halogens. So you'll notice that we wrote down fluoride, but we didn't write down any of the other halogens. They are usually -1. So if I have it combined with a metal, if I have cobalt chloride, iron chloride, it's going to be -1. And usually in our non-metal compounds, phosphorus chloride, nitrogen chloride, it would also be -1. But if it is combined with oxygen, or if it is combined with another halogen, then I've got some different rules. So an interhalogen is 2 halogens in the compound. And when that happens, the one that is lighter or furthest up on the periodic table gets to be -1 like it wants to be, and got to figure out the other one with algebra. Okay, so what does that look like? Remember that in compounds, it's going to add up to whatever the overall charge is. So if I have iodine pentachloride, I'm first going to ask myself, which is the lighter one, iodine or chlorine? Chlorine is higher up on the periodic table. So chlorine gets to be a -1. So we usually write the oxidation number as a small number right above the symbol. Okay. Then I'm going to create a little algebra problem for myself. Iodine +5 times -1 is equal to the overall charge, which is 0. Okay. So iodine -5 equals 0. And this is where people get thrown sometimes. They see that -5 and they're like, oh, it's -5. But if I did -5, -5, I'd have -10, right? So just for the sake of remembering how algebra works, we have to add 5 to both sides. And I'm getting really low on the board here. So iodine is equal to +5. Okay? That's how we would do that with algebra. In contrast, if I were going to do, say, NaCl, sodium, and we follow these rules in order. So if two rules conflict, you follow the rule that's higher up. So the first rule says, or the second rule says that for group 1, sodium is going to be +1. So that has to be true. And then for my chlorine, it's probably going to be -1, but I'm going to go down to this rule and I'm going to say, oh, halogens with metals are -1. And then I double check, is 1 minus 1 equal to 0? Yeah, so that works out. Okay. So I have put at your tables little Post-it notes that have different elements. And so you are going to work with the people at your table. And Maggie, I'm going to have you move over to this table over here so you're not working by yourself, to find the thing that is not oxygen or hydrogen. So your rule is going to be oxygen is -2, hydrogen is -1. So I'm going to do an example here with nitrite, because we didn't do one with our nitrate because we didn't do a charged one. So NO3 minus, this is -2. So nitrogen plus -2 for the oxygen times 3 is equal to -1. Okay. Then I'm going to say the nitrogen -6, so I'm just combining those, is equal to -1. So is nitrogen going to be -7? No. We have to add 6 to both sides, and nitrogen is +5. Okay, so once you sort that out, you're going to take this over to this board over here, and you're going to put on the board underneath the oxidation number for that non-oxygen, non-hydrogen element. Okay, now if you have, I don't know how many of these there are, if you have something that has 2 of them. So for example, this one says Mn2O3. Then you have to divide by 2 for this. So my oxygen is -2. So I would say 2 manganese plus -2 times 3 is equal to 0. So 2 manganese -6 equals 0. So manganese is not 6, but it's 3. I had to divide by 2. Okay, so if you have a 2 in there, that's how you solve for that. All right. So take a few minutes and get your Post-it notes up there, and then we'll check them, and then we'll talk about when oxidation and reduction happen in chemical reactions. Good oxidizing agents have high oxidation numbers. So they're going to be like +5, +6, +7, and possibly have a lot of oxygens. So when we have chemicals like a nitrate, that's NO3 minus, that's a good oxidizing agent. It has 3 oxygen, it's in the +5 oxidation state. Or perchlorate, it has 4 oxygens in the +7 oxidation state. These are good oxidizing agents, and we keep them away from other chemicals because oxidizing and reduction reactions can be very energetic. Like this, with this, that was so energetic it creates a fire. So we don't want to have spontaneously mixing chemicals causing fires in our stock rooms. So we separate out the good oxidizing agents so they don't accidentally get mixed up with other things that it might react with. So important to know what good oxidizing agents are. All right, that is chapter 4. On Monday, we're going to get to gas laws. Hopefully I'll have your test to get back to you. Have a good weekend.